My name is Rung-Bin. My talk is about improving pin accessibility of standard cell libraries in 7 nanometer technology. The co-authors are my master students. Rung-Bin is a professor in the Department of Computer Science and Engineering at Yuan Ze University, Taiwan. He received a PhD degree in computer science from the University of Minnesota. His research interests focus on the area of electronic design automation, including physical design, timing analysis, and low-power designs. This is the outline of the talk. Pin access is about connecting an external wire to the pins of a standard cell, typically by a wire from M2 layer to an M1 pin, preferring ungripping access with a wire being placed at the intersection of an M1 track and an M2 track. Here we have two ungripping accesses, and here we have two off-gripping accesses, and here we have a pin access through taping an M1 wire. The basics of laying out a pin include making an input pin as long as possible, reducing access conflicts between adjacent pins, placing pin at the position that enables ungripping access. Finally, we have to handle possible conflicts among the above three goals. For example, moving pin A2 to this position, it will enable ungripping access of A2. However, it creates access conflicts between A1 and A2. Pin access challenge may be due to use of low cell height or intrinsically tied to process technology. For example, in this work, we will use ASAP7 PDK technology. This technology specifies a contacted polypitch of 54 nanometer and an M1 pitch of 36 nanometer. Because 54 is not a multiple of 36, this causes a problem of not being able to achieve 100% ungripping accesses. The problem of using low cell height is short vertical segment of a pin. Here we have a 6-track cell. A2, B2, and B1 have very short vertical segment. If we do not pull A1 to the left, A1 will have also very short vertical segment. The problem tied to technology is as follows. Here we have two instances from the same cell. The 3 pins on the left instance are all on track M3 track that enable ungripping access, whereas the 3 pins on the right instance are all off from M3 tracks that makes ungripping access impossible. As a result, we are not able to achieve 100% ungripping access. In the past, there are a number of approaches to pin access problem. During placement, we can perform cell shifting, cell flipping, cell swapping, directing area between cells or doing cell displacement. During cell design, different pin footprints for the same cell can be created and selectively used by a appraiser to improve pin accessibility. In this work, we propose several approaches to pin access problem. This include refining pin layout, using double rawhide cells, using double rawhide cells with mass-joint pins, inserting dummy pulleys into cells with hard-to-access pins, excluding cells with poor pin accessibility from a cell library. In this work, cell layouts are designed with virtuoso layout editor and characterized by libret. Both tools are from Cadence. We use the following refining techniques to improve a 6-track cell library. First, place a vertical M1 wire on the M3 track as possible as it can be. Place a horizontal M1 pin wire on an M2 track as possible as it can be. Prefer a vertical M1 pin wire than a horizontal M1 pin wire if they offer the same number of access points. Balance the number of pin access points among all the pins in a cell as possible as it can be. Increase the length of a horizontal M1 pin wire if the vertical M1 pin wire is too short. Increase access point of an input pin as possible as it can be. Use M2 pin wires if M1 pin wires cannot provide enough access point. The improved cell library is called C6LM. The cells in this table are laid out with double row heights. In each layout, M2 wires are aligned on the same track as possible as they can be to minimize the number of M2 tracks used. For example, here we have one big full adder. As one can see here, the M2 wires on this layout are aligned on the same track as possible as they can be. We call this cell library C6LDR. For each double rawhide cell with mass-joint pins, instead of having all net pins completely routed, we dedicate a chip-level router to complete routing of across row net. We call this library C6LDRM. For example, here we have a cross row net. Its routing should be completed by a chip-level router. The cells in this table are inserted with dummy pulleys to improve pin accessibility. The number in the pair of the parentheses is the number of pulleys inserted. For example, here, this is the original layout, and this is the layout being inserted with 2 dummy pulleys. We call this cell library C6L+. The cells in this table are excluded from C6LM to form a cell library called C6L-. We use the above 5 approaches to create 5 6-track cell libraries, respectively. All the library except C6L- have the same number of cells. This table shows the average number of access points per pin. As one can see here, C6LM has the smallest number of access points per pin, whereas C6L plus has the largest number of access points per pins. This table shows pros and cons of these cell libraries in terms of diffusion break at the boundary, aspect ratio, cell size, pin accessibility, cell diversity. Double row height cells use more cell area for creating diffusion breaks at the cell boundary. Although we do not use more cell area to create diffusion break at the boundary for a cell in C6L-. However, a design synthesizes with C6L- will have more cells. This corresponds to have more diffusion breaks. In terms of aspect ratio, cell size, pin accessibility, and cell diversity, the pros and cons are more or less obviously. We will not discuss them here. We have two types of evaluation. The first one is to see which library will be able to attain maximal code utilization. The second evaluation is to see which cell library will have best total wire length and the view count under the premise of using the same code utilization. This flowchart shows the experimental flow for our evaluation. We first synthesize the benchmark circuit using a 6.5 track cell library. Then we replace the cells of the 6.5 track cells with the 6 track cells in the corresponding cell library. And then we do press and route, and then we collect the denied data. For the cell library C6L-, we cannot use this flow because some cells are excluded from this library. So we directly synthesize a benchmark circuit with C6L-, and then we do the press and route using Innovus from Cadence. These are the benchmark circuit used for our evaluation. The total number of cells ranges from 18,000 cells to 190,000 cells. The number of double row high cells in design with these two libraries takes about 5% of the total number of cells. The number of directed cells in designs with C6L+ takes about 32%. This table shows the maximum co-utilization attained by each cell library. All the data except WNS and the TNS are normalized to the data obtained with C6LM. As one can see here, C6L plus achieved the highest co-utilization. C6L minus also achieves the highest co-utilization, but the circuit with this library uses 16% more cells and 20% more cell areas. This table shows the variance and the view count under the premise of using same co-utilization. As one can see here, C6L plus achieved the smallest TW plus view count. The next smallest is C6LM, whose TWL plus view count is equal to 2. C6L minus has the best WNS. In this work, we look into pin access challenge intrinsically tied to ASAP7 PDK. We also present 5 approaches to improving pin accessibility of standard cells designed with ASAP7 PDK. 5 6-track cell libraries are designed accordingly. We found out inserting dummy polys into hard-to-access cells and the refining pin layouts are 2 more effective approaches. Thank you for your attention. This is my email.